such that for, let's say, points x, y belonging to the first space A, the distance in that space, the images of x and y is distance measured in this space in x and y, x1 property. Okay, so isometry, if you will. Look at what this is saying. It's saying if I look at the distance between 2 points in A, then that distance is preserved in the image space under the metric refinement of the image space. Okay? But there's a second part. Also for U, V, and V, distance in that metric, G, U, G, V, is distance in this metric of U, V. So, isometry is requires that this distance preserving goes in both directions. And now there is a theorem that I'll state about isometry. I'm not going to prove it. A necessary and sufficient condition, if and only if that two metric spaces be isometric, spaces A with its metric and B with its metric be isometric, is that there exists a function f which takes A into B such that 1, f is 1, 1. Everyone knows what a 1, 1 function is, I know. Which means if it's 1, 1, then it has an inverse. 1, 1 inverse exists. Okay, f is 1, 1. F is onto, it's an onto function. And then for x, y in A, the distance in the B space, x, y, is distance. Okay, so these three conditions guarantee that two metric spaces are isometric. Function is 1, 1 onto, and because and of course this distance or metric preserving the 1, 1 onto gives you this property. So this definition of isometric spaces is kind of expressed more compactly, if you will, here. So we now have a definition of isometry. Okay? And we'll come back to that. So I just kind of give you. Fortunately, we've got to kind of throw out, establish a certain amount of basic definitions, and so we have some ammunition. said, not every topological space is induced or derivable or connected to a metric space, but in the case of the real line, it's an example of a association of a topological space with a metric space. Okay, and I think probably the simplest example, or the most concrete one that you'd be able to wrap your brain around would be the real line. This is R1. This is a topological space. And as I said earlier, this will be kind of our laboratory for looking at a lot of these topological concepts, the real line. You've been looking at the real line over 2 semesters of calculus, so we'll look at it as a point of view of it being a topological space. But it's a topological space arising from the metric space consisting of the real line with the very familiar metric D, where the D is just the absolute value of the distance between the A and B are an R, is just absolute value of A minus B, R. Okay, so this is I think this is an example that you can kind of relate to. There is some fancy vocabulary. We should talk about a collection of topological spaces